What if I told you we're prisoners? Tonight, we're going to explore the invisible cage surrounding our entire solar system, a cosmic boundary no human has ever crossed. You've probably heard about space exploration, maybe even dreamed of traveling to distant stars. But here's what most people don't realize. We're actually trapped inside a massive bubble, stretching 1.5 light years in every direction. By the end of this journey, you're going to understand why this boundary exists and why it might be the ultimate limit of human expansion. Before we dive in, if you enjoy these cosmic explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. This is going to be mind-bending. Picture this. A spacecraft unlike any we've ever built accelerates away from Earth, carrying with it the sensation of finally escaping our confining planetary cradle. The engines burn fuel with an efficiency never before achieved in human history, pushing humanity toward territories never explored by our physical bodies. The Earth shrinks rapidly in the rear window, transforming itself into an increasingly distant blue dot against the black void. In just 8 hours, the moon passes by like a pale memory, its familiar craters disappearing as the ship gains unprecedented velocity. You can almost feel the psychological weight lifting as that gravitational anchor we call home becomes just another point of light behind you. Think about that for a moment. Everything you've ever known, every person you've ever met, every mountain you've climbed and ocean you've crossed, now fits within a pixel of light, barely visible through the ship's sensors. Mars emerges and vanishes within mere weeks, its famous dust storms invisible in the growing distance of this accelerated journey. The asteroid belt dissolves into scattered points of light, millions of rocks reduced to occasional glimmers without threat. These objects that once seemed so substantial, so dangerous in our imaginations, are now just fireflies drifting through an ocean of emptiness. Jupiter appears like a striped ball the size of a full moon, then shrinks to a bright star within a few months. Saturn and its magnificent rings shine briefly, that 300,000-kilometer structure reduced to a distant luminous point. The orbital paths of the outer planets become mathematical abstractions, invisible circles that exist only in maps and computer simulations. As the months turn into years, something profound begins to happen. The familiar landmarks of our solar system neighborhood start to lose all meaning. These planets we've studied, dreamed about, sent robots to explore, they're becoming mathematical concepts rather than real places. Neptune marks the traditional boundary of our solar system, that final gas giant sitting 4.5 billion kilometers from the Sun. But the ship continues forward, and at 18 billion kilometers, it encounters something called the heliopause, where the solar wind meets the interstellar medium in an invisible frontier. Here's where things get interesting. The solar wind at this distance contains only 5 protons per cubic centimeter, a density 10 trillion times smaller than the air you're breathing right now. The temperature has dropped to minus 270 degrees Celsius, cold enough to freeze carbon dioxide into dry ice. The sun's light is still visible, but it has lost its quality as the dominant source of illumination, becoming just another bright star among thousands. The ship continues its advance, systems functioning perfectly, maintaining that steady velocity of 20 kilometers per second through constant thruster operation. 6 months pass since launch, and the distance traveled already exceeds 3 billion kilometers beyond distant Neptune. After one complete year of travel, the ship crosses Pluto's most distant orbit at 5.9 billion kilometers. The instruments show only darkness ahead. No significant objects appear on the long-range sensors available for detection, and here, the imaginary crew begins to perceive something that fundamentally changes their understanding of space itself. You see, the space between stars isn't just large. It's fundamentally different from everything we know. 2 years after launch, the ship reaches 12 billion kilometers, officially entering the hypothetical distant Oort cloud. This region contains trillions of frozen comets, but they're so dispersed that the probability of seeing even one is practically zero. The density here is approximately one mountain-sized object for every billion cubic kilometers of empty space. Let me put that into perspective. If you were standing in a room the size of a football stadium and there was exactly one grain of sand somewhere in that entire space, you'd have a better chance of finding that grain than this ship has of encountering a comet. 3 years into this journey, the calculations reveal a devastating truth about that 20 kilometer per second velocity the ship has achieved. This speed represents only 0.07% of the speed of light. In cosmic terms, this is absolute slowness. Light travels 300,000 kilometers in a single second. The distance that takes light 1 second to cover requires 4 full hours for our ship to traverse. And here's where the numbers become truly humbling. Proxima Centauri, the nearest star to our solar system, sits 40 trillion kilometers away. At our ship's impressive velocity, reaching Proxima would require more than 63,000 years of continuous travel without stops or detours. 5 years since launch, and the ship finally reaches 1 light-year distance, 9.5 trillion kilometers from Earth. 1 light-year is the distance light travels in a year, but our ship needed 5 years just to cover that distance. And then it happens, the impact against the invisible. Not a physical collision, you understand, but a mathematical perception that is both implacable and inescapable. The crew, studying their instruments and running their calculations, suddenly comprehends the true nature of their situation. They haven't hit a wall made of matter or energy, but something far more absolute. The wall they've encountered is made of distance itself. Pure, unforgiving distance, multiplied by the absolute scarcity of matter, energy, and human time. There are no refueling stations out here, no planets to mine for resources, absolutely nothing except growing emptiness. Picture trying to swim across an ocean where all the water has been removed, leaving only the abstract concept of distance. That's what confronts them now. The ship could continue forward for decades, centuries even, and encounter essentially nothing. The probability of finding even a single rock larger than your fist in the next 1,000 years of travel is essentially zero. The nearest star still lies 3 times further than the entire distance they've traveled in 5 long years. The ship would need another 15 years just to reach the 1.5 light-year mark, and that's assuming perfect mechanical function and unlimited fuel supplies. But here's what makes this invisible wall so absolute. Even if they had unlimited fuel, even if the ship never broke down, even if the crew could somehow survive the journey, the laws of physics themselves conspire to make this endeavor impossible. Einstein's special relativity establishes that nothing can travel faster than 300,000 kilometers per second. This isn't just a speed limit, it's a fundamental property of spacetime itself. Accelerating mass to light speed would require infinite energy, making it impossible by the very definition of relativistic physics. Even at 99% of light speed, the ship would experience severe time dilation, where time slows relative to the universe. For the crew, the journey might seem to last decades, but on Earth, centuries would pass, destroying any connection with their origin. The return trip would take another 5 years minimum, assuming perfect trajectory reversal without additional energy loss. Communication with home now requires 1 full year just for a message to travel one way, another year for any response to return through the void. Any conversation becomes a temporal abstraction, a ghostly connection across distance that destroys the normal concept of simultaneous dialogue. But perhaps most devastating of all is the realization that this invisible wall wasn't placed here by any external force. It emerges directly from the fundamental structure of the universe itself, from the very laws that govern matter, energy, space, and time. The speed of light isn't an arbitrary limit that some future genius will discover how to circumvent. It's a direct consequence of space-time geometry, of how the universe is literally constructed at its most fundamental level. The distances between stars weren't chosen randomly by some entity. They emerge from the natural process of stellar formation. Stars form in giant molecular clouds that fragment into dense regions under their own gravity over millions of years. Each fragment collapses separately, creating individual stars surrounded by disks of material that later form planets. The typical distance between these fragments, and therefore between stars, is determined by the physics of turbulent molecular clouds. This physics isn't negotiable or modifiable. It emerges from fundamental laws of gravity, thermodynamics, and quantum mechanics. As the imaginary crew sits in their ship, still moving forward but now understanding the true nature of their situation, they realize they've crossed a threshold. Not a physical one, but a practical limit of human exploration. This limit isn't written on signs or marked on maps. It simply emerges from the consistent application of physical laws. The invisible wall they've encountered defines not just the boundary of possible human travel, but the edge of meaningful human presence in the cosmos. Beyond this point, the universe becomes not just distant, but fundamentally disconnected from human timescales, human energy resources, and human technological capabilities. And so the ship continues forward into the growing darkness, its crew now understanding that they're not explorers pushing into new territory. The invisible wall has no substance. It cannot be touched or detected by sensors, yet it exists absolutely as a fundamental limit. The calculations spread across the ship's screens reveal a truth more devastating than any physical barrier could ever be. The distance to Proxima Centauri still stretches 3 times farther than the entire journey already completed over 5 long years. The ship would need another 15 years merely to reach the 1.5 light-year mark from our central shining sun. 1.5 light-years represents approximately 14 trillion kilometers. This number transcends completely any terrestrial reference available to human comprehension. If you could count 1 kilometer per second without stopping, without sleeping, without eating, it would take you 443,000 years just to reach that number. Think about that for a moment. 443,000 years ago, modern humans hadn't even emerged from Africa. Our entire species, everything we've built, everything we've discovered, all of human history from the first cave paintings to space travel, represents a fraction of the time it would take just to count the distance we're trying to cross. The Oort cloud extends to approximately 2 light-years from the Sun, still gravitationally bound to the star that warms us, or technically, the ship remains within this cloud, but the probability of seeing any object is smaller than finding one specific grain of sand on an entire beach. Imagine walking along the coastline of an entire continent, searching for one particular grain among trillions. That's the likelihood of encountering even a mountain-sized comet in this vast emptiness. The sensors sweep constantly through the space ahead, searching for any sign of matter, radiation, or structure detectable by available technology. Nothing appears except the distant glow of stars that still lie years light beyond the ship's possible reach. These stars, appearing as mere points of light, mock the vessel with their inaccessibility. Each one represents a destination that would require not decades, but centuries or millennia to reach. And here's where the wall reveals its true nature. The fuel supply is depleting rapidly, and even if it were infinite, accelerating further encounters the absolute fundamental limits of nature itself. The Tsiolkovsky rocket equation, formulated by the Russian pioneer over a century ago, shows that final velocity depends on the exhaust velocity of the propellant and the mass ratio. To reach merely 10% of light speed using chemical rockets, the ship would need to be 99% fuel. Picture that. For every kilogram of useful cargo, crew quarters, life support, and scientific equipment, you'd need 99 kilograms of pure chemical fuel. But the implications extend far beyond simple ratios. Chemical rockets produce exhaust velocities of roughly 4 kilometers per second at their theoretical maximum. To achieve the relativistic speeds necessary for interstellar travel, you need exhaust velocities approaching significant fractions of light speed itself. Chemical bonds simply cannot release enough energy per unit mass to make this possible. Even 10% of light speed would still require 42 years to reach Proxima Centauri, more than an entire professional career. A person launching at age 25 would arrive at age 67, assuming perfect survival without accelerated aging. But decades in space bring their own devastating challenges. Studies of astronauts on the International Space Station show that microgravity causes bone density loss of approximately 1% per month. After 42 years in zero gravity, a human skeleton would be so weakened that returning to any planetary surface with significant gravity would be physically impossible. The bones would simply shatter under their own weight. Muscle atrophy occurs even faster than bone loss, with astronauts losing roughly 2% of muscle mass per month in weightlessness. Nuclear propulsion could theoretically achieve a few percent of light speed. But no such system has been tested successfully at real scale. The engineering challenges of containing nuclear reactions in the vacuum of space, maintaining reactor integrity over decades of operation, and managing radiation shielding for a human crew remain essentially unsolved. Nuclear fission reactors require massive shielding to protect human occupants from lethal radiation. This shielding adds tremendous weight to the spacecraft, reducing efficiency precisely when maximum efficiency is needed. Nuclear fusion would be far more efficient, but we haven't yet achieved sustained fusion reactions that produce more energy than they consume, even in laboratory conditions on Earth. Antimatter propulsion would convert mass completely into energy according to Einstein's famous equation. But we currently produce only 10 nanograms of antimatter per year in our most advanced terrestrial particle accelerators. 10 nanograms, that's 10 billionths of a gram, an amount invisible to the naked eye even under a powerful microscope. 1 kilogram of antimatter annihilating with 1 kilogram of matter would release energy equivalent to 43 megatons of TNT. The total energy released would equal roughly 850 times the atomic bomb dropped on Hiroshima. We would need tons of antimatter for interstellar travel, a quantity trillions of times larger than our current annual production. At present rates, accumulating enough antimatter would require millions of years of continuous production. But storing antimatter presents its own impossible challenges. Antimatter annihilates instantly upon contact with normal matter, so it must be contained in perfect magnetic fields that never fail. The slightest malfunction would release nuclear-level explosive energy, vaporizing the spacecraft and everything aboard. The invisible wall reveals itself as being constructed from pure distance multiplied by the absolute scarcity of matter, energy, and available human time. There are no refueling stations out here, no planets to mine for resources, absolutely nothing except growing emptiness that stretches infinitely in every direction. It's like trying to swim across an ocean where all the water has been removed, leaving only the abstract concept of distance itself. You can move your arms and legs all you want, but there's nothing to push against, no medium to support your progress. The space between stars is so empty that if you scaled down the solar system until Earth was the size of a marble, the nearest star would still be thousands of kilometers away. The imaginary crew finally understands that they have crossed a threshold. Not a physical limit, but the practical boundary of definitively possible human exploration. This limit isn't written on signs or marked on maps. It simply emerges from the laws of physics applied consistently across cosmic distances. Einstein's special relativity establishes that nothing can travel faster than 300,000 kilometers per second. This represents a fundamental limit, not a technological challenge to be overcome. The speed of light isn't just a speed limit, it's the speed of causality itself. Information cannot propagate faster than light, which means the universe has a built-in delay between cause and effect across cosmic distances. Accelerating mass to light speed would require infinite energy, making it impossible by the very mathematical definition of modern relativistic physics. As you approach light speed, your mass approaches infinity, requiring ever-increasing amounts of energy to accelerate even slightly faster. It's not that we lack powerful enough engines. The universe itself forbids this possibility. Even at 99% of light speed, the ship would experience severe time dilation, where time itself slows relative to the universe. For the crew aboard, the journey might seem to last decades, but on Earth, centuries would pass, destroying any connection with their known origin. Picture the psychological weight of that realization. You leave Earth as part of human civilization, connected to family, friends, culture, shared history. But when you arrive at your destination, everyone you've ever known is dead. The languages you speak might be extinct. The countries you remember might have vanished from maps. You've become a temporal refugee, displaced not just in space, but in time itself. The return journey would require another 5 years minimum. Assuming perfect trajectory reversal without additional energy loss, but communication with home now takes 1 full year just for a message to travel one way, another year for any response to return through the void. Any conversation becomes a temporal abstraction, a ghostly connection across distance that destroys the normal concept of simultaneous dialogue between people. Imagine trying to maintain a relationship when every exchange takes 2 years minimum. By the time you receive their response to your question, you've forgotten why you asked it. By the time they receive your reply, they've moved on to entirely different concerns, possibly even different stages of life. The medium through which signals must travel is almost perfectly empty. The interstellar medium contains approximately 1 atom per cubic centimeter, compared to Earth's atmosphere with 10 billion molecules in the same volume. Radio waves propagate through this near vacuum at light speed, but they spread and weaken according to the inverse square law. A signal that seems strong when transmitted becomes whisper faint across interstellar distances. The power required to maintain communication over light years would drain the ship's energy reserves, energy desperately needed for life support, propulsion, and basic survival systems. Even the most powerful radio telescopes on Earth can barely detect signals from our most distant space probes when they reach the edge of the solar system. But perhaps most profoundly, the invisible wall reveals something fundamental about the universe's structure. The distances between stars weren't chosen randomly. They emerge from the natural physics of stellar formation, where giant molecular clouds fragment into star-forming regions under gravitational collapse over millions of years. These fragments separate naturally across multiple light years, creating the typical spacing we observe throughout the galaxy. This isn't a bug in the universe's design, it's a feature, a consequence of how gravity, thermodynamics, and turbulence interact on cosmic scales. The universe could not be organized any other way, and still form stars, planets, and the complex chemistry necessary for life. The wall that contains us isn't malicious. It's simply the way space and time are organized at the largest scales. Just as gravity prevents us from flying off Earth's surface through pure willpower, the structure of space-time prevents us from casually hopping between stars. The universe has built-in isolation between stellar systems, ensuring that each island of potential life develops independently, and so the ship continues forward, its crew now fully comprehending their situation. They're not explorers pushing into new territory. They're witnesses to the fundamental isolation that defines every intelligent species' place in the cosmos. The universe may be vast beyond imagination, but each island of life remains forever isolated on its own shore, separated by oceans of emptiness too vast to cross. The invisible wall has revealed itself as an absolute frontier. Now the narrative abandons the fantasy completely and returns to where humanity actually stands at this exact moment in history. The imaginary spacecraft fades away, along with its impossible journey and theoretical crew. What remains is the stark reality of our true position in the cosmic ocean. Earth continues orbiting the Sun in the same trajectory it has followed for billions of years, completing one revolution every 365 days, carrying us all through space at 30 kilometers per second without anyone feeling the motion. We're passengers on a planet that never stops moving, yet we experience it as perfectly still. No crewed spacecraft has ever traveled beyond the Moon, that familiar celestial companion sitting just 384,000 kilometers from Earth's surface. In the grand scheme of interstellar distances, the Moon might as well be in our backyard. The International Space Station orbits a mere 420 kilometers above us, so close that you can see it with your naked eyes as it passes overhead on clear evenings. If Earth were a basketball, the ISS would orbit less than 1 centimeter from its visible outer surface. Think about that scale for a moment. Our most advanced permanent human outpost in space sits closer to Earth than the distance between many cities. If you could drive straight up at highway speeds, you'd reach the ISS in about 4 hours. It's not even truly in space in any meaningful sense. It's still well within Earth's protective atmosphere, surrounded by the same gravitational field that holds your feet to the ground right now. The Apollo missions represent our maximum crewed reach. Between 1969 and 1972, 12 human beings walked on the lunar surface. These missions, humanity's greatest achievement in space exploration, carried astronauts to the Moon and safely back again. But in terms of interstellar distance, traveling to the Moon is equivalent to taking a single step outside your front door in a transcontinental journey. All human footprints on lunar soil fit within an area smaller than 5 football fields combined. Every place a human being has ever stood beyond Earth could fit inside a modest suburban neighborhood. The farthest any crewed spacecraft has ever traveled was approximately 1 light second from Earth. Not light years as we imagined in our fantasy, but 1 single second. 1 light second equals 300,000 kilometers, exactly the average Earth-Moon distance. In galactic terms, this represents practically zero distance. Our robotic probes have ventured farther, but even they remain trapped within the invisible bubble that confines us collectively. Voyager 1, launched in 1977, has been traveling continuously since then without stopping or slowing down. It represents humanity's most distant physical presence in the universe. Currently, Voyager 1 sits approximately 24 billion kilometers from Earth, the absolute record for any deliberately manufactured human object. This distance represents roughly 0.26% of a single light year, a microscopic fraction of the journey necessary to reach even our nearest stellar neighbor. To put this in perspective, if our entire solar system were the size of a coin, Voyager 1 would still be within the thickness of the metal. The probe has traveled for nearly 5 decades, outlasting most of the engineers who built it, and yet it has barely begun to scratch the surface of true interstellar space. Technically, Voyager 1 has entered interstellar space, but only in the sense that it has passed beyond the heliopause, where the solar wind meets the interstellar medium. The heliopause sits approximately 18 billion kilometers from our central sun. Beyond this boundary begins what astronomers technically call the space between stars, but calling this interstellar represents extreme linguistic generosity. The probe remains gravitationally bound to our sun, still within the vast sphere of solar influence. The Oort cloud, that hypothetical shell of comets surrounding our solar system, extends possibly 1 to 2 light-years from the sun. Voyager 1 would require another 300 centuries just to completely traverse this cloud. The probe travels at approximately 17 kilometers per second, a velocity achieved by using the gravity of Jupiter and Saturn as a gravitational slingshot. This represents the fastest speed any human-made object has ever sustained over interstellar distances. At this impressive velocity, Voyager 1 would still require 73,000 years to reach the proximity of any other star in the night sky. But Voyager 1's electrical systems will fail completely around 2025, silencing communication forever and irreversibly. The probe will then become merely an artificial rock drifting through the void, without consciousness of its own silent journey through the cosmos. Pioneer 10 sits even farther away in terms of mission duration. Launched in 1972, it blazed a trail toward the outer solar system that Voyager would later follow. Its last signal reached Earth in January 2003, when the spacecraft was approximately 12 billion kilometers from home. Now, Pioneer 10 exists beyond our reach of communication, a technological ghost wandering without possibility of contact or operational status verification. We know it's out there somewhere, coasting through the darkness, but we've lost touch forever. It has become the first human artifact to achieve true isolation from its creators. New Horizons, the spacecraft that visited Pluto in July 2015, continues advancing at approximately 58,000 kilometers per hour. That sounds impressively fast until you calculate the implications. Even at this remarkable velocity, New Horizons would require 81,000 years to reach Proxima Centauri. Imagine that timeline. 81,000 years ago, modern humans were just beginning to migrate out of Africa. Cave paintings were still millennia in the future. Agriculture wouldn't be invented for another 70,000 years. The entire span of recorded human history, from the first written records to space travel, represents roughly 5,000 years. All these probes combined represent the absolute maximum extent of physical human presence in the known observable cosmos. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, New Horizons. These 5 ambassadors of humanity carry our species farther than we ourselves can ever go. Yet even collectively, they barely register on cosmic scales. If you imagine the distance to Proxima Centauri as a journey from New York to Los Angeles, our farthest probe has traveled approximately the width of a single city block. We're not just at the beginning of interstellar exploration. We haven't even taken the first meaningful step. The signals from these distant emissaries grow weaker each year. Radio waves obey the inverse square law, meaning signal strength decreases proportionally to the square of the distance. A signal that seems strong when transmitted becomes whisper faint across the solar system. The Deep Space Network, our most sensitive collection of radio telescopes, strains to hear the faintest whispers from our most distant machines. When Voyager's last signal finally fades to nothing, we'll lose our most distant eyes and ears in the universe. The probe will continue its journey in complete silence, carrying a golden record with sounds and images from Earth. But no one will ever know where it goes or what it encounters. These spacecraft represent something profoundly moving about human nature. We built machines capable of outlasting civilizations and sent them toward destinations we can never reach ourselves. In a sense, they're our most permanent monuments, more lasting than pyramids, more enduring than mountains. But they also represent the hard boundaries of human expansion. Despite our finest engineering, our most ambitious dreams, our greatest technological achievements, we remain confined to an almost impossibly small corner of a single solar system. The space between stars isn't just vast. It's designed by the fundamental laws of physics to remain forever beyond our reach. These robotic explorers will drift through the cosmic dark long after human civilization has transformed beyond recognition. They'll outlast our languages, our countries, possibly our entire species, yet they'll never reach another star, never send back images of another world with life, never fulfill the dreams that inspired their creation. The distances involved transcend not just our technology, but our biology, our psychology, our entire existence as temporal beings. We live for decades in a universe measured in billions of years. We think in human lifespans, while space operates on cosmic timescales. This fundamental mismatch isn't a problem to be solved. It's a feature of reality itself. Together, all these probes represent the absolute maximum extent of physical human presence in the cosmos observable to us today. And that extent, impressive as it seems from our planetary perspective, amounts to essentially nothing when measured against the true scale of interstellar space. To truly understand our cosmic confinement, we need to examine the geometry of our prison. The entire solar system, including the Oort cloud, has a radius of approximately 2 light-years from the central shining sun that warms us. 2 light-years equals 19 trillion kilometers, a distance that completely defines our current invisible cosmic prison. If we could somehow view this bubble from the outside, it would appear as an almost perfectly empty sphere with the sun as a minuscule central point. The density within this enormous volume averages approximately 1 atom per cubic centimeter, 10 trillion times less dense than the air you're breathing right now. Let me help you visualize this emptiness. The air around you contains roughly 10 billion molecules per cubic centimeter. In interstellar space, you might find a single hydrogen atom in that same volume. Its emptiness so profound that it surpasses the best vacuum chambers we can create in terrestrial laboratories. If we could somehow remove all the empty space from the atoms within this 2 light-year bubble, all the matter would fit into a cube just a few kilometers on each side. Imagine compressing 19 trillion kilometers worth of space into something smaller than a city. That's how empty our cosmic neighborhood truly is. The total mass of the Oort cloud is estimated at approximately 3 Earth masses, dispersed throughout this absolutely colossal, immeasurable volume. 3 Earth masses equals 18 nonillion kilograms, a number with 30 zeros after the initial one. Try to count to 1 nonillion. If you counted one number per second without stopping, it would take you longer than the current age of the universe. But this material is so dispersed that the probability of any 2 particles colliding is practically zero during billions of years. You could place yourself randomly anywhere within the Oort cloud and drift for geological ages without encountering so much as a grain of dust. The sun gravitationally dominates everything within this 2 light-year bubble, maintaining comets and objects in extremely elliptical orbits that stretch across unimaginable distances. At 2 light-years distance, the sun's gravity is approximately 1/billionth the strength of Earth's surface gravity. Yet this minuscule tug is sufficient to keep objects orbiting for billions of years without escaping to true interstellar space. Think about the patience of cosmic mechanics. A comet at the edge of the Oort cloud might take millions of years to complete a single orbit around the sun. From its perspective, our star appears as just another point of light, barely distinguishable from other stars. Yet that distant gravitational whisper guides its path across eons of time. Beyond 2 light-years, the gravity of other stars begins to compete with our Sun, defining the real boundary of solar gravitational dominance. Proxima Centauri sits 4.24 light-years away, which means there exists a transitional gravitational region between the stars. In this region, objects might be pulled by either the Sun or Proxima, creating a dynamically complex zone of shared gravitational influence. But even this transitional region represents nearly perfect vacuum, without significant matter to explore or utilize as available resources. The nearest star after Proxima is Alpha Centauri A, part of a triple star system at roughly the same general distance. Alpha Centauri B orbits around A, while Proxima orbits the distant pair, creating a complex gravitational dance that unfolds over millions of years. The combined mass of the Alpha Centauri system equals approximately 2 solar masses, just slightly more than our isolated bright Sun. After them, the next star is Barnard's star at 6 light-years distance, further increasing our spatial isolation. Sirius, the brightest star in our night sky, lies 8.6 light-years away, almost twice as distant as Proxima. From our perspective, Sirius appears brilliant and nearby. But it's actually farther than we could travel in multiple lifetimes, even at relativistic speeds. Of the 50 nearest stars, most lie between 5 and 15 light-years from our known solar system. These 50 stars occupy a volume of approximately 1,000 cubic light-years, creating a stellar density of roughly 1 star per 20 cubic light-years. To truly grasp this isolation, imagine our Sun as a basketball sitting in São Paulo. Proxima Centauri would be another basketball in Buenos Aires, Argentina. The other nearby stars would be scattered across all of South America, Mexico, and Central America, demonstrating our absolute extreme isolation. In this analogy, the planets would be invisible grains of sand orbiting the basketballs, too small to see clearly even if you knew exactly where to look, and all of humanity would fit within a single atom on the surface of the grain of sand representing Earth. Insignificance beyond comprehension. But even at this reduced scale, the distances between stars remain vast, empty, and insurmountable with any currently imaginable technology. The emptiness doesn't disappear when you shrink the model. It persists at every level of scaling. Consider the journey between our basketball in São Paulo and the one in Buenos Aires. Even flying at jet aircraft speeds, the trip takes hours and crosses thousands of kilometers of varied landscape, cities, rivers, and mountains. Now imagine that same journey, but through absolute vacuum. No air to breathe, no landmarks to navigate by, no possibility of stopping or changing course. The 1.5 light-year bubble where our imaginary ship encountered its invisible wall sits well within our sphere of gravitational influence. But it marks the point where technological realism meets practical impossibility, where exploration fantasy collides with implacable physics. Beyond this point, we not only haven't arrived yet, we probably never will arrive with conscious, living, human physical presence. The energy requirements, the time scales involved, the fundamental physics limitations all conspire to make such journeys essentially impossible. But here's what makes our confinement so psychologically challenging. The barrier isn't obviously there. When you look up at the night sky, stars appear tantalizingly close, bright points of light that seem almost within reach. Your brain, evolved for terrestrial distances, interprets these lights as nearby objects. The reality is profoundly different. Each point of light represents a nuclear furnace so distant that its light left before human civilization began. The patterns we see in constellations exist only from our specific viewpoint. Stars that appear close together might actually be separated by hundreds of light years. Our nearest stellar neighbors in the Alpha Centauri system appear to the naked eye as a single point of light. 3 massive stars, an entire stellar system, possibly containing planets and complex chemistry, reduced to an anonymous dot, indistinguishable from thousands of others. The psychological impact of this realization can be overwhelming. We live in a universe teeming with stars, planets, and possibilities. Yet we're forever isolated on our small blue world, able to observe, but never to visit these cosmic wonders. But perhaps there's beauty in this limitation. Our confinement also represents protection, insulation from the violent cosmic forces that rage between the stars. Solar radiation, cosmic rays, supernovae explosions. The void between stars is hostile to life as we know it. Our 2-light-year bubble isn't just a prison, it's also a sanctuary. Within this sphere, the sun's influence creates a relatively stable environment where planets can form, where liquid water can exist, where complex chemistry can evolve into biology and eventually consciousness. The invisible wall doesn't need to be solid to be absolutely effective in confining us within this defined cosmic prison. Distance itself, combined with the fundamental laws of physics and the limitations of human biology, creates a barrier more impermeable than any material wall could ever be. But the space between stars isn't completely empty, as our imagination might suggest. It contains what astronomers call the interstellar medium, composed primarily of dispersed hydrogen atoms drifting through the cosmic void. The interstellar medium has an average density of approximately 1 atom per cubic centimeter in typical regions of our galaxy. Compared to Earth's air, which contains 10 to the 19th power molecules per cubic centimeter, this represents almost perfect absolute vacuum. The emptiness is so profound that it challenges our terrestrial understanding of what empty actually means. To put this in perspective, imagine trying to find a single person in an area the size of the entire United States, and that person is invisible, weightless, and randomly moving. That's roughly the density of matter you'd encounter in typical interstellar space. In denser regions called molecular clouds, the density can reach millions of atoms per cubic centimeter. Yet even these dense regions still qualify as vacuum by any earthly standard. A molecular cloud that seems substantial to astronomers would still represent emptiness more complete than the best vacuum chambers we can create in our laboratories. If you could somehow collect all the interstellar material between here and Proxima Centauri, it would fit into a mountain roughly the size of Sugarloaf Mountain in Rio de Janeiro. 40 trillion kilometers of space contain less matter than a 400-meter-tall mountain, revealing the extreme absolute emptiness that defines the cosmic void. But this seemingly insignificant dispersed material creates serious problems for spacecraft traveling at relativistic velocities approaching the maximum speed of light. At these extreme speeds, even individual atoms become formidable obstacles. At 10% of light speed, a single hydrogen atom impacts with the energy of a powerful rifle bullet. The relative velocity is so enormous that the collision releases kinetic energy comparable to high-powered ammunition. Imagine your spacecraft being sandblasted by invisible bullets traveling at cosmic velocities. At 30% of light speed, that same hydrogen atom impacts with energy equivalent to a hand grenade exploding on the ship's surface. The spacecraft would need to survive constant bombardment by explosions too small to see, but powerful enough to damage or destroy critical systems. At 90% of light speed, a simple atom becomes a cosmic ray capable of penetrating meters of solid metal shielding. The hydrogen nucleus, accelerated to near light speed by the ship's motion, carries enough energy to punch through the most robust armor we could conceivably construct. A dust particle the size of a grain of sand, impacting at 90% of light speed, would release energy equivalent to a small nuclear bomb. The explosion would vaporize not just the impact site, but potentially the entire spacecraft and everyone aboard. The faster you travel, the more dangerous the universe becomes. An interstellar spacecraft would require massive frontal shielding, drastically increasing both mass and the energy necessary for efficient acceleration. But here lies a fundamental paradox without any obvious available solution. Heavy shielding makes it impossible to reach the relativistic velocities necessary for reasonable travel times. You need extreme speed to make interstellar travel feasible. But extreme speed makes the journey lethal without extreme protection. The protection makes extreme speed impossible. It's a perfect catch-22 written into the structure of physics itself. Beyond scattered matter, the interstellar medium contains cosmic radiation from supernovae, pulsars, and the distant active galactic core. These cosmic rays represent some of the most energetic phenomena in the universe, accelerating particles to velocities approaching light speed. Cosmic rays are charged particles traveling near the speed of light, with energies that can reach billions of electron volts. An electron volt represents the energy an electron gains when accelerated through 1 volt of electrical potential, a minuscule unit that multiplies absurdly when discussing cosmic phenomena. To understand the scale, a single cosmic ray particle can carry more energy than a baseball thrown at 60 miles per hour, concentrated into a space billions of times smaller than an atom. When such particles strike matter, they can trigger cascades of secondary radiation that penetrate deeply into solid materials. Cosmic rays with billions of electron volts can pass completely through a human body, damaging DNA and exponentially increasing the risk of fatal cancer. A single high-energy cosmic ray can break chemical bonds in dozens of molecules along its path, potentially triggering genetic mutations or cellular death. During a journey lasting decades through interstellar space, accumulated exposure would prove lethal without adequate shielding constantly protecting the crew. But shielding against cosmic radiation requires meters of water, metal, or dense composite materials, adding tons of mass to the spacecraft. Magnetic fields could deflect charged particles, but would require massive superconducting coils, consuming energy continuously without ever stopping. The power requirements for maintaining protective magnetic fields across interstellar distances would rival the energy needs of entire cities. Energy that must come from the spacecraft's finite power systems. The temperature of the interstellar medium hovers extremely low, approximately 3 degrees Kelvin above absolute zero, the fundamental limit where all molecular activity ceases completely. 3 Kelvin equals minus 270 degrees Celsius. Cold enough to freeze any known substance instantly. At these temperatures, metals become brittle as glass. Rubber and plastics shatter like ice, and even steel can crack from thermal stress. Any spacecraft venturing into true interstellar space would need heating systems capable of maintaining livable temperatures against the infinite cold sink of the universe. Solar radiation keeps objects near the sun warmed. So temperature becomes problematic only far from any nearby star. But once beyond our sun's influence, the cosmic cold becomes relentless, requiring constant energy expenditure to prevent everything from freezing solid. The pressure of the interstellar medium is practically zero, approximately 10 to the negative 17th atmospheres, representing vacuum superior to any laboratory on Earth. In this near-perfect vacuum, any hull breach would prove catastrophic, emptying breathable atmosphere in minutes or seconds, depending on the hole's size. Maintaining structural integrity during decades or centuries of travel would represent a colossal challenge without precedent in known human engineering. Materials fatigue, thermal cycling, radiation damage, and the constant stress of maintaining pressure differentials would gradually weaken any spacecraft structure. Micrometeorites, particles roughly the size of salt grains, travel at tens of kilometers per second through interstellar space constantly. Impact from a micrometeorite would equal a bullet passing through a wall, creating holes and possibly damaging critical survival systems. The spacecraft would require massive redundancy in all systems, multiplying complexity and mass far beyond any currently imaginable existing project. Every critical component would need backups, and those backups would need backups, because failure in deep interstellar space means death with no possibility of rescue. Consider the psychological challenges as well. Decades of isolation in a confined space, surrounded by lethal vacuum and bombardment by invisible radiation. The crew would need to maintain complex life support systems while knowing that any major malfunction means certain death. Far beyond any hope of assistance from Earth, the interstellar medium also contains weak magnetic fields, approximately 1 microgauss, roughly 1 million times weaker than Earth's magnetic field. These fields might seem insignificant, but across galactic distances, they can deflect charged particles, creating complex and unpredictable radiation patterns. Navigating through these invisible magnetic territories would be like sailing through ocean currents you cannot see, where changing conditions could unexpectedly concentrate deadly radiation or alter the paths of cosmic rays. The magnetic environment between stars remains largely unknown, another variable that could prove fatal to unprepared travelers. These magnetic fields also interact with the solar wind, creating boundaries and shock waves where different magnetic domains meet. The heliopause, where our solar wind meets the interstellar medium, represents just one such boundary. Beyond our local stellar neighborhood, similar boundaries exist between the influences of different stars. All these factors combine to make the interstellar medium not just empty space to be crossed, but an actively hostile environment that becomes more dangerous the faster you attempt to traverse it. The void between stars doesn't passively allow passage. It actively opposes any attempt at high-speed transit. These weak magnetic fields can deflect charged particles across gigantic distances, creating complex and always unpredictable radiation patterns that would challenge any spacecraft attempting to navigate the interstellar void safely. Yet, despite these formidable obstacles, human ingenuity continues proposing solutions, each one eventually encountering its own insurmountable barriers. Solar sails use light pressure to accelerate spacecraft without requiring fuel. But the force generated is extremely weak for any significant mass. Solar radiation pressure at Earth's orbit equals approximately 9 micropascals, a minuscule force compared to any known chemical propulsion system. A solar sail the size of a football field carrying just 1 kilogram of mass would accelerate at merely millimeters per second squared. To put this in perspective, it would take months just to reach the speed of a walking person. The acceleration is so gentle that atmospheric drag on Earth would completely overwhelm it. To achieve relativistic velocities, the sail would need to span kilometers in diameter, while the spacecraft mass could total only grams. Imagine constructing a mirror larger than most cities, yet so delicate that the entire payload weighs less than a smartphone. The engineering challenges of deploying and maintaining such a structure in space appear virtually impossible. Consider the material requirements alone. A sail kilometers across must be nearly perfectly reflective, yet thin enough to achieve an acceptable mass-to-area ratio. Any microscopic tear or wrinkle would compromise the entire structure. In the vacuum of space, there's no atmosphere to provide damping against vibrations, so the slightest disturbance could cause catastrophic oscillations across the entire sail. Temperature variations across such a large structure would create thermal stresses. The side facing the sun might heat to hundreds of degrees, while the shadowed portions drop to near absolute zero. These temperature differentials would constantly flex the material, eventually leading to metal fatigue and structural failure. The Breakthrough Starshot project represents humanity's most serious attempt at interstellar exploration, proposing to send miniature probes to 20% of light speed using concentrated terrestrial laser systems. The concept requires a 100-gigawatt laser array focused on thumbnail-sized spacecraft. 100 gigawatts equals the combined output of 100 large nuclear power plants operating simultaneously at full continuous capacity without interruption. To put this energy requirement in perspective, 100 gigawatts represents roughly 8% of the entire electrical generating capacity of the United States. This massive power output would need to be sustained for 10 full minutes, consuming enough electricity to power millions of homes for hours, all focused on accelerating a single gram of matter. The probe would be roughly the size of a paperclip, weighing only 1 gram, equipped with a reflective sail just a few atoms thick. This represents the absolute minimum payload capable of carrying even rudimentary sensors and communication equipment. Everything humans have ever built in space would seem gigantic compared to these proposed vehicles. But even this minimal payload faces enormous challenges. How do you fit a camera, computer, transmitter, and power source into something weighing less than a paperclip? The entire Apollo command module weighed over 5,000 kilograms. The proposed Starshot probe weighs 6 million times less while attempting a journey millions of times farther. The laser would need perfect pointing accuracy for 10 minutes while the probe accelerates. Precision impossible with current atmospheric technology. Atmospheric turbulence constantly deflects laser beams, the same phenomenon that makes stars appear to twinkle. To achieve the required precision, the laser array would need construction in space or perfect synchronization across multiple ground-based facilities. Building the laser array in space would require launching thousands of tons of equipment, along with the infrastructure to maintain and operate it. Ground-based arrays would need to compensate for atmospheric distortion, requiring adaptive optics systems more advanced than anything currently existing, even assuming perfect technological execution. The probe faces additional challenges during acceleration. As it gains speed, the relative frequency of the laser light changes due to the Doppler effect. The sail's reflectivity depends on the light's wavelength, so acceleration efficiency would decrease over time. The probe must also survive the intense laser bombardment. 100 gigawatts focused on a gram of matter creates extreme heating. The sail material must reflect nearly all incident light, because absorbing even a tiny fraction would vaporize the entire probe instantly. Even achieving 20% of light speed, the probe would reach Proxima Centauri in 20 years, but without any ability to slow down completely. Without fuel for braking, the probe would flash past the stellar system in just a few hours at 60,000 kilometers per second. During this brief flyby, it might capture some photographs and basic measurements, but couldn't explore planets or enter stable orbit. The flyby velocity presents its own problems. At 60,000 kilometers per second, even taking a photograph becomes challenging. The probe's tiny cameras would need incredibly fast shutter speeds to avoid motion blur, while simultaneously gathering enough light for useful images across interstellar distances. Transmitting data back to Earth would require another 4 years for signals traveling at light speed through the interstellar void. And after crossing 40 trillion kilometers, those signals would be extraordinarily weak, requiring enormous antenna arrays to receive the encoded message. The probe's tiny transmitter would be attempting to communicate across distances that make our solar system seem microscopic. The signal strength follows the inverse square law, meaning it weakens proportionally to the square of the distance. A signal that seems strong at Earth becomes whisper faint at Proxima Centauri. The probe's transmitter, constrained by its 1 gram mass limit, could generate only milliwatts of power. Nuclear fusion propulsion could theoretically achieve 10% of light speed, with advanced technology still decades or centuries from development. Fusion reactions require temperatures of 100 million degrees Celsius, 10 times hotter than the core of our shining sun. These extreme temperatures must be magnetically confined within small volumes. A challenge humanity hasn't solved despite 70 years of consistent attempts. The plasma becomes so hot that it would instantly vaporize any material container, requiring magnetic fields strong enough to hold stellar core temperatures in invisible bottles. The magnetic containment systems consume enormous amounts of energy, often more than the fusion reactions produce. Current experimental reactors require external power to maintain the magnetic fields, making them energy sinks rather than sources. ITER, our largest experimental reactor, will begin operation in the 2030s, hoping to demonstrate fusion reactions that produce more energy than they consume. But ITER weighs 23,000 tons and occupies the volume of a large building, completely impractical for lightweight, efficient spacecraft design. The reactor's massive weight comes from the superconducting magnets, which must be cooled to near absolute zero while containing plasma at stellar temperatures. The thermal isolation systems alone weigh thousands of tons. The entire structure must withstand enormous magnetic forces that would otherwise crush the reactor. Building a fusion reactor light enough for interstellar vessels would require technology centuries beyond what we currently possess. The reactor would need to maintain stellar temperatures while weighing mere tons rather than thousands of tons. Every component would need to be simultaneously more efficient and more durable than anything in our current technological repertoire. The fuel handling systems present additional challenges. Fusion reactors consume deuterium and tritium, isotopes of hydrogen that must be stored and delivered to the reaction chamber with extreme precision. The fuel injection systems must operate reliably for decades without maintenance in the harsh environment of interstellar space. Antimatter engines would convert mass completely into energy, according to Einstein's famous equation EMMC2, achieving theoretical 100% efficiency, but antimatter annihilates instantly upon touching normal matter, requiring containment in perfect magnetic fields that never fail. Currently, we produce only 10 nanograms of antimatter annually in Earth's most advanced particle accelerators. 10 nanograms equals approximately 10 billionths of a gram, an amount invisible to the naked eye even under powerful microscopes. The annual global production of antimatter wouldn't power a light bulb for more than a few seconds. The production process itself reveals the impossibility. Creating antimatter requires enormous particle accelerators, consuming gigawatts of electricity. The energy required to produce antimatter exceeds the energy it can release by factors of millions, making it the most inefficient fuel source imaginable. We would need kilograms or tons of antimatter for interstellar voyages, quantities trillions of times larger than current annual production. At present, manufacturing rates accumulating enough antimatter would require millions of years of continuous operation from every particle accelerator on Earth. The slightest failure in magnetic containment would detonate all stored antimatter, with the explosive force of multiple Hiroshima-sized nuclear weapons simultaneously destroying everything nearby. Imagine carrying a bomb more powerful than any nuclear arsenal where the tiniest malfunction triggers instant annihilation. The containment systems must operate perfectly for decades in the radiation-filled environment of interstellar space, with no possibility of repair or maintenance. A single cosmic ray striking the wrong component could cause catastrophic failure, turning the spacecraft into a brief, brilliant explosion visible from Earth. Wormholes appear as potential shortcuts through spacetime and general relativity theory, but remain purely speculative constructs without observational evidence. The mathematical equations permit wormhole solutions, but maintaining one open would require exotic matter with negative energy density. Negative energy has never been observed in nature at macroscopic scales, existing only as microscopic quantum fluctuations in vacuum. The Casimir effect demonstrates negative energy between closely spaced metal plates. But the quantities involved are infinitesimally small. The quantities necessary for traversable wormholes would equal the energy mass equivalent of entire stars. Impossible to manipulate or artificially generate with any conceivable technology. You would need to harvest the mass energy of multiple suns, then somehow convert it into a form of matter that may not even exist. Warp drives, popularized by science fiction like Star Trek, would bend space-time around the spacecraft, creating a bubble of curved space that moves faster than light while the ship remains stationary within it. The Alcubierre metric shows mathematically how warp drives might work, but the original formulation requires negative energy equivalent to the mass of Jupiter. This impossibility places such technology forever beyond reach, forcing us to confront a humbling reality about our place in the cosmic hierarchy. In 1964, Soviet physicist Nikolai Kardashev created a scale to classify civilizations by the energy they control. His framework provides a stark measurement of humanity's current limitations and our distance from any meaningful interstellar capabilities. A Type 1 civilization controls all energy available on its planet, approximately 10 to the 16th watts of continuous power. 10 to the 16th watts equals 10,000 trillion watts, roughly 1,000 times humanity's current energy consumption. Think about that multiplication factor for a moment. We would need to increase our energy production by 1,000 times to reach Type 1 status. That means building the equivalent of 1,000 times our current power infrastructure. Every nuclear plant, every solar farm, every hydroelectric dam, multiplied by 1,000. To put this in perspective, if every person on Earth had their own nuclear power plant, we still wouldn't approach Type 1 energy levels. We would need to fundamentally transform how we generate, distribute, and consume energy. Developing technologies that currently exist only in theoretical papers. Current global energy consumption hovers around 18 trillion watts, drawn primarily from fossil fuels with growing but still modest contributions from renewable sources. Coal still powers much of human civilization, while nuclear energy, despite its enormous potential, provides only about 10% of global electricity. A Type 1 civilization wouldn't just consume more energy. It would harness energy sources we've barely begun to exploit. Geothermal energy from Earth's core could power civilization for millions of years. Fusion reactors could convert seawater into fuel, providing clean energy for geological time spans. But even these advances pale beside the energy requirements for interstellar travel. A single mission to Proxima Centauri using current rocket technology would consume more energy than human civilization produces in decades. We're not just short of the energy needed for interstellar travel. We're orders of magnitude away from even beginning to approach it. A Type 2 civilization controls all energy from its star, approximately 10 to the 26th watts captured completely and continuously. Our Sun emits roughly 384 septillion watts of power, a number with 26 zeros after the initial digit. To truly comprehend this scale, imagine that every square meter of Earth's surface was covered with the most efficient solar panels possible. Even then, we would capture only a tiny fraction of the Sun's total output. The vast majority of solar energy radiates uselessly into empty space, heating nothing, powering nothing. To capture this stellar energy, a Type II civilization would need to construct a Dyson sphere, a structure completely surrounding the star to collect all radiated energy. Freeman Dyson proposed this concept in 1960, not as a solid shell which would be gravitationally unstable, but as a swarm of energy-collecting satellites. Imagine the engineering challenges. Millions of satellites, each larger than Earth, orbiting at different distances and velocities around the Sun. The construction materials alone would require dismantling entire planets. Jupiter's mass might provide enough material for the supporting infrastructure. The logistics stagger the imagination. Coordinating the construction of millions of satellite platforms across the entire solar system, each one precisely positioned to avoid collisions while maximizing energy collection. The project would take thousands of years, requiring technological stability and social organization beyond anything human civilization has demonstrated. A Type III civilization controls energy from an entire galaxy, approximately 10 to the 36th watts or more of available power. The Milky Way contains roughly 200 billion stars, each emitting energy equivalent to or greater than our central sun. The total galactic energy would be approximately 100 billion times the energy of a single star, a scale absolutely incomprehensible to human understanding. Try to visualize 100 billion Dyson spheres, each harvesting the complete output of a star. Their combined energy controlled by a single technological civilization. Such a civilization could literally reshape galaxies, moving stars into more convenient arrangements, harvesting the energy of stellar collisions, even manipulating black holes as power sources. They could build structures visible from other galaxies, engineered constructions spanning thousands of light years. Humanity currently rates approximately 0.73 on the Kardashev scale. We haven't even achieved Type I status yet. We consume about 18 trillion watts currently, drawn mainly from fossil fuels, with some renewable and nuclear sources available. This means we're closer to pre-industrial civilization than to Type Is. Our energy consumption has grown dramatically in the past century, but we remain fundamentally limited by our reliance on chemical energy sources. Even our most advanced technologies, nuclear reactors and solar panels, barely scratch the surface of what's physically possible. To reach Type I, we would need to multiply our energy capacity by a factor of approximately 50s. This means not just building 50 times more power plants, but developing completely new energy sources and distribution systems. Every aspect of our energy infrastructure would require revolutionary transformation. Carl Sagan proposed a formula for calculating exact position on the scale, using logarithms of a civilization's total observed energy consumption. According to this formula, we might reach Type I in approximately 200 years. If energy growth continues at historically observed rates. But energy growth has slowed in recent decades. Economic development in wealthy nations has decoupled from energy consumption, while environmental concerns limit expansion of fossil fuel infrastructure. The transition to renewable energy proceeds slowly, constrained by technology costs and political resistance. Climate change adds another complication. Rapidly increasing energy consumption using current technologies would accelerate global warming beyond manageable levels. We might need to solve the carbon emission problem before we can pursue the massive energy increases required for Type I status. Even a Type I civilization would remain trapped in the same interstellar bubble. Planetary energy proves insufficient for crude relativistic travel. The energy required to accelerate a spacecraft to significant fractions of light speed exceeds the output of entire continents. Projects like laser sailing require Type 1 energy levels just to send tiny probes, not crewed vessels with living humans. Consider the Breakthrough Starshot project again. 100 gigawatts, focused for 10 minutes to accelerate a paperclip-sized probe to 20% of light speed. This represents roughly 8% of current U.S. electrical generating capacity. Devoted to launching a single gram of matter, a crewed mission would require millions of times more energy. A spacecraft capable of supporting human life during an interstellar journey would weigh thousands of tons. Accelerating this mass to relativistic speeds would require energy equivalent to the output of entire stars. Even Type 1 civilizations couldn't attempt such missions. A Type 2 civilization could theoretically construct fleets of interstellar spacecraft, but would still require centuries to reach nearby available stars. Even controlling the sun's complete energy output doesn't violate fundamental physics limits, such as the maximum speed of light or the necessity of accelerating mass. With stellar-level energy resources, a Type 2 civilization could build generation ships, massive habitats capable of supporting thousands of people during century-long journeys to nearby stars. These ships would be artificial worlds, complete with ecosystems, manufacturing facilities, and everything needed for independent existence. For meaningful interstellar travel, we would need Type 2 energy just to move a few crewed ships with basic resources. The energy cost of accelerating even small spacecraft to relativistic velocities demands stellar-level power generation. A single interstellar mission might consume more energy than human civilization produces in centuries. But Type 2 civilizations face their own limitations. Even with complete control over stellar energy, they remain bound by the fundamental physics of space-time. The speed of light creates absolute barriers that no amount of energy can overcome. Distance and time continue to impose their tyrannical rule. Colonizing an entire galaxy would require a Type 3 civilization, with resources to launch millions of ships in all directions, simultaneously over millennia. But even Type 3 remains confined within its galaxy. The distance to Andromeda stretches 2.5 million light-years. Type 3 civilizations might seem godlike to us, but they face the same fundamental constraints that bind all matter and energy. They cannot violate causality, cannot exceed light speed, cannot escape the geometric prison of space-time itself. Their power, however vast, operates within the same physical laws that limit our modest capabilities. No amount of energy permits faster than light travel. So, Andromeda will always remain millions of years distant. The speed of light isn't merely a velocity limit. It's the speed of causality itself, the fundamental structure of known relativistic space-time. Information cannot propagate faster than light, meaning a civilization in Andromeda could never coordinate actions with a civilization in the Milky Way. Radio signals sent today would reach Andromeda in 2.5 million years. Any response would require another 2.5 million years to return. 5 million years ago, human ancestors were Australopithecus, walking upright but possessing brains of only 400 cubic centimeters. They used simple stone tools and had no language, no agriculture, no technology. The entire span from Australopithecus to space travel represents less time than a single round-trip communication with Andromeda. No known civilization endures millions of years without transforming into something completely different, culturally and technologically. Human societies change dramatically within centuries, sometimes within decades. The civilization that sends a message to Andromeda would be extinct long before receiving any reply. Consider the pace of technological change in just the past century. In 1924, radio was cutting-edge technology and computers didn't exist. Air travel was experimental, spaceflight was pure fantasy. The society that existed 100 years ago would barely recognize our current civilization, projecting this rate of change forward. The civilization that exists in 1,000 years will be as alien to us as we are to medieval peasants. After millions of years, any resemblance to the original society would be purely coincidental. The message senders and message receivers would be different species entirely. The barrier isn't merely energetic, but also temporal. Cosmic timescales transcend completely any known human social structure. Even with infinite energy, time remains a prison as effective as distance, confining us within our local bubble of space and time. Proxima Centauri lies 4 light-years distant, meaning any event occurring there becomes known to us only 4 years later. But even if we somehow develop technology to accelerate a spacecraft to 10% of light speed instantaneously, without any energy cost, Proxima Centauri would still require 42 years of continuous travel, a time span longer than a typical complete human professional career. A person launching at age 20 would arrive at 62, assuming perfect survival without any additional accelerated aging. This represents the absolute best-case scenario, ignoring the brutal reality of what 4 decades in space would do to a human body. Studies conducted on the International Space Station reveal that microgravity causes bone density loss of approximately 1% per month. After 42 years in zero gravity, an astronaut's bones would be so weakened they couldn't support their own body weight under Earth's gravity. The skeleton would literally crumble under the stress of standing upright. Muscles atrophy even faster than bones, losing approximately 2% of mass per month in weightless environments. Without constant resistance exercise, muscle tissue wastes away at rates that make recovery impossible. After 4 decades, the human body would become a fragile shell of its former self. The cardiovascular system suffers equally severe degradation. In microgravity, the heart doesn't need to pump blood against gravity, so it weakens dramatically. Blood volume decreases, bone marrow stops producing red blood cells efficiently. The circulatory system that once supported an active human becomes barely adequate for basic survival. Accumulated cosmic radiation during decades of travel would increase cancer risk to nearly 100%. Death becomes almost guaranteed eventually. Unlike Earth's protective magnetosphere and atmosphere, interstellar space offers no shielding from high-energy particles streaming from supernovae and galactic phenomena. Each cosmic ray impact damages DNA. Most damage gets repaired by cellular mechanisms, but the repair process itself becomes less efficient over time. Accumulated mutations eventually trigger cancerous growth. The longer the journey, the more certain the biological catastrophe. The immune system weakens significantly in space, making astronauts more susceptible to infections that would be trivial on Earth with robust immune responses. Minor cuts become serious wounds. Common bacteria become life-threatening pathogens. Medical emergencies that could be easily treated planetside become fatal complications in the isolation of deep space. Psychological isolation during decades with the same few people creates serious documented mental health problems. Studies of prolonged confinement on Earth show increasing rates of depression, anxiety, paranoia, and interpersonal conflict. These problems intensify in environments where escape is impossible, where personal space is minimal and privacy non-existent. The second nearest star, Sirius, lies 8.6 light-years away. Doubling the travel time to 86 complete years, no one departing for Sirius would live to see their return to Earth, creating permanently unidirectional voyages with no possibility of homecoming. and this assumes that no one on Earth cares about waiting 86 years to receive news from the distant travelers. But civilizations change drastically over decades, let alone nearly a century of constant accelerated technological and cultural transformation. Ancient Rome at its height lasted approximately 1,000 years, but changed completely several times during that extended historical period. The Rome of Julius Caesar would be utterly unrecognizable to the Romans of Constantine 1,000 years later. They spoke different languages, practiced different religions, and operated under completely altered political structures. Caesar's Rome was a republic transitioning to empire, worshipping traditional gods, speaking classical Latin, governing through senatorial traditions. Constantine's Rome was a Christian empire, speaking late Latin approaching medieval languages, governing through imperial bureaucracy, centered in Constantinople rather than the original city. Expecting any civilization to maintain a space project for a full century represents an immense challenge, let alone for thousands or millions of years. Political systems rise and fall, technologies become obsolete, cultural priorities shift dramatically. The society that launches an interstellar mission might be extinct before the spacecraft reaches its destination. Consider how much human civilization has changed in just the past century. In 1924, most people lived without electricity, automobiles were luxury items, and flight was still experimental. The idea of space travel existed only in science fiction. Our current world would be incomprehensible to people from that era. Most stars visible to the naked eye lie between 50 and 500 light-years from our home Earth. At 1,000 light-years distance, a journey at 10% of light speed would require 10,000 years, equivalent to all recorded human history contained in documents. 10,000 years ago, humans were just beginning agriculture in the Fertile Crescent, still without writing systems or complex organized cities. If those first farmers had departed for a star 1,000 light-years away, they would be arriving now at their originally planned distant destination. Think about the profound transformation that represents. The civilization that launched the mission practiced primitive agriculture and lived in simple villages. The civilization receiving news of arrival builds computers, explores space, and manipulates matter at the atomic level. No continuity exists between departure and arrival cultures. The Milky Way spans 100,000 light-years in total diameter. Crossing it at 10% of light speed would require 1 million years. 1 million years ago, Homo erectus walked through Africa, still without controlled fire or fully developed articulated complex language. From 1 million years ago until now, multiple different human species emerged and disappeared, including Neanderthals and Denisovans, who are now extinct. No technology, language, culture, or social structure endures 1 million years without transforming into something completely unrecognizable from its origin. Even assuming generation ships where multiple generations are born and die aboard during the endless journey through cosmic void, the temporal challenges remain insurmountable. After 1,000 years of isolation, the ship's culture would be completely different from Earth's, possibly no longer speaking the same ancestral original language. Language evolution occurs constantly. Modern English differs dramatically from the English spoken just 500 years ago. Shakespeare's plays required translation for contemporary audiences. After a millennium of isolation, shipboard language would diverge beyond mutual comprehension. After 10,000 years, the passengers would become a biologically different species, adapted to zero gravity and artificial closed environments. Genetic drift and natural selection would create a population distinct from Earth humans, possibly incapable of reproducing with their terrestrial cousins after any hypothetical impossible return. Human populations isolated for thousands of years developed distinct genetic characteristics. The ship's inhabitants would adapt to their unique environment, developing different bone density, muscle mass distribution, possibly even organ modifications. They would become aliens in human form. All this assumes we could maintain humans alive in closed environments for thousands of consecutive years without complete systemic collapse. Our largest experiment in closed habitat living, Biosphere 2, failed after only 2 years with 8 people voluntarily isolated in Arizona. Oxygen levels dropped dangerously low. Carbon dioxide accumulated to toxic concentrations, pests destroyed food crops, and psychological conflicts nearly destroyed the mission completely. The participants experienced severe weight loss, chronic fatigue, and interpersonal tensions that threatened violence. And this occurred in a facility on Earth with the possibility of immediate evacuation if necessary. A generation ship would face identical challenges, but magnified across centuries or millennia, with no possibility of rescue or evacuation. Every system must function perfectly for longer than human civilization has existed. Any failure means death for everyone aboard. The life support systems would require maintenance and replacement over geological timescales. Machinery wears out, components fail, materials degrade, even the most robust systems need periodic overhaul. On a generation ship, the inhabitants must manufacture everything from raw materials, including replacement parts for systems they may no longer understand. Consider the complexity of modern technology. No single person understands how to build a computer from raw materials. The knowledge is distributed across thousands of specialists, each expert in narrow domains. A generation ship crew would need to maintain this distributed knowledge across centuries of isolation, but knowledge degrades without use. Skills disappear when not practiced. Written records deteriorate, oral traditions change with each telling. After several generations, critical knowledge might be lost forever, leaving the ship's inhabitants unable to repair essential systems. The psychological challenges compound over time. Each generation grows up knowing they will die aboard the ship, never seeing the destination their ancestors chose. Resentment builds against decisions made by people long dead. Why should children born in space sacrifice their lives for goals they never chose? Rebellion becomes inevitable. Some generation might decide to turn around, or stop, or change course entirely. Others might sabotage the mission deliberately, preferring to end the endless journey rather than continue suffering for dreams they don't share. And this scenario was in an installation on Earth with the possibility of immediate abandonment if necessary, not a ship distant light years from home without any option for rescue or escape. The devastating final realization is that this barrier doesn't reflect any temporary failure of our technology or lack of human ambition. It's not a matter of waiting 100 or 1,000 years until we develop better engines or discover revolutionary new physical principles. The barrier emerges directly from the fundamental structure of the universe itself, from the very laws that govern matter, energy, space, and time. The speed of light isn't merely an arbitrary speed limit that some future genius will eventually discover how to circumvent. It's a direct consequence of space-time geometry, of how the universe is literally constructed at the most fundamental level possible. Einstein demonstrated in 1905 that space and time aren't absolute but relative, intertwined in a single unified structure. Within this framework, the speed of light remains constant in all reference frames, an inevitable mathematical consequence of Maxwell's equations describing electromagnetism. Violating the light speed limit would be equivalent to making 2 + 2 = 5. A logical contradiction impossible within the structure of reality itself. The speed of light isn't just fast, it's the speed at which causality propagates through the universe. When you flip a light switch, the electrical signal travels through the wire at roughly the speed of light. When you see a star, the light has traveled at exactly light speed from its source to your eyes. When you hear thunder after lightning, sound travels much slower than light. But light itself represents the absolute maximum speed at which information can move through spacetime. Consider what this means for the structure of reality. Every interaction between particles, every force that holds atoms together, every chemical reaction that powers life, all operate at speeds limited by light. The electromagnetic force that binds electrons to nuclei propagates at light speed. The weak nuclear force that powers stellar fusion operates at light speed. Even gravity, according to general relativity, propagates as gravitational waves, traveling at exactly light speed. The universe operates as a vast computer, with light speed representing the maximum clock rate at which information can be processed and transmitted. Just as your computer's processor has a maximum frequency beyond which it cannot operate, the universe itself has a maximum information processing speed built into its fundamental architecture. Even theoretical wormholes, if they existed, wouldn't violate relativity, but would use extreme space-time curvature predicted by Einstein's equations. But the curvature necessary would require energy densities greater than the core of the densest known neutron star. Neutron stars possess density of 400 trillion grams per cubic centimeter. Matter so compressed that a teaspoon would weigh as much as Mount Everest. This represents the densest possible matter before gravitational collapse into a black hole. The protons and neutrons are pressed so tightly together that the star becomes essentially a giant atomic nucleus spanning kilometers. Yet wormholes would require densities infinitely greater. Energy densities that would make neutron stars seem as empty as interstellar space by comparison. We're talking about concentrating the mass-energy equivalent of multiple stars into regions smaller than atomic nuclei, creating conditions that may be mathematically possible, but physically impossible to achieve. Wormhole maintenance would demand negative energy, violating all known energy conditions in theoretical physics. No evidence exists in nature that negative energy occurs in the macroscopic quantities necessary for practical manipulation. The Casimir effect demonstrates negative energy, but only between atomic scale plates in laboratory conditions. The negative energy required for traversable wormholes would need to be stable, controllable, and maintainable across cosmic distances. We would need to manufacture and manipulate a form of matter that behaves opposite to everything we observe in nature. It's not just technologically challenging, it may represent a fundamental impossibility encoded in the laws of physics. The distances between stars weren't chosen randomly by some entity. They emerge from the natural process of stellar formation that we observe throughout the universe. Stars form within giant molecular clouds that fragment into dense regions under their own gravity over millions of years. Each fragment collapses separately, creating individual stars surrounded by disks of material that later form planetary systems. The typical distance between these fragments, and therefore between mature stars, is determined by the physics of turbulent molecular clouds. Think about this process, Wos. Giant clouds of gas and dust, spanning hundreds of light years, slowly contract under their own gravity over millions of years. Turbulence within these clouds creates density variations. Some regions become slightly denser than others, and these denser regions attract more material. The spacing between these density peaks depends on the cloud's temperature, composition, and turbulent motions. All of these factors are governed by fundamental physics, thermodynamics, fluid dynamics, and gravitational dynamics operating on cosmic scales. This physics isn't negotiable or modifiable. It emerges from fundamental laws of gravity, thermodynamics, and quantum mechanics that are firmly established. We can't wish these laws away or engineer around them. They define the basic operating principles of reality itself. The gravitational constant determines how strongly masses attract each other. Boltzmann's constant governs how thermal energy relates to temperature. Planck's constant sets the scale at which quantum mechanics becomes important. These aren't arbitrary human conventions, but discovered properties of the universe that appear to be the same everywhere and at all times. Galaxies also possess structure determined by physics, not by choice. Flattened disk shapes arise inevitably from the conservation of angular momentum. As matter collapses under gravity, any initial rotation causes it to spin faster and faster, until centrifugal force balances gravitational attraction in a thin disk. It's the same physics that makes pizza dough flatten when spun, but applied on scales of hundreds of thousands of light years. The cook doesn't choose to make the dough flat. Rotation and physics make flattening inevitable. Conservation of angular momentum is one of the most fundamental laws in physics, discovered through careful observation of planetary motions and formalized through centuries of mathematical analysis. This law applies equally to spinning ice skaters, rotating galaxies, and collapsing stars. The universe doesn't make exceptions for objects that would prefer different shapes. The void between stars is equally unavoidable. Matter tends to aggregate under gravity, leaving empty space between the aggregations. It's impossible to distribute matter uniformly because gravity is unstable. Any region slightly denser than average pulls in more matter, creating exponential growth of density differences. This gravitational instability operates on all scales, from the formation of planets within stellar systems to the clustering of galaxies across cosmic distances. Even if the universe began with perfectly uniform matter distribution, quantum fluctuations would create tiny density variations that gravity would amplify over time. The universe inevitably develops a spongy structure, with matter aggregated in galaxies and vast emptiness between them. This represents a fundamental pattern observed at all scales, from the spacing of planets around stars to the distribution of galaxy clusters across cosmic distances, computer simulations of cosmic evolution. Starting from nearly uniform initial conditions and applying only gravity and known physics, automatically reproduce the large-scale structure we observe. The cosmic web of galaxies, the vast voids between them, the typical scales of clustering, all emerge naturally from the mathematics without requiring any special design or fine-tuning. The barrier that confines us isn't a wall someone built maliciously. It's the inevitable consequence of how the universe functions at its most basic level. Complaining about interstellar distances is like complaining about gravity keeping us bound to Earth's surface. Gravity isn't a choice, but a consequence of mass-distorting spacetime. It prevents us from flying into space arbitrarily without effort, but we don't consider this a conspiracy or failure of engineering. We accept gravity as a fundamental feature of reality and work within its constraints. We build rockets that overcome gravity through brute force, applying enough energy to escape Earth's gravitational well, but we can't build rockets that ignore gravity or pretend it doesn't exist. We must work within the constraints that physics imposes. Similarly, the structure of spacetime and interstellar distances confine us within our local bubble. This represents fundamental physics in action, not some temporary obstacle awaiting a technological solution. Consider how every proposed solution to interstellar travel eventually encounters these same fundamental barriers. Chemical rockets lack the energy density required by the rocket equation. Nuclear engines require materials and containment systems that push the boundaries of what's physically possible. Antimatter engines demand exotic matter in impossible quantities. Solar sails work only for microscopic payloads over enormous time frames. Each failure points to the same underlying truth. The universe is structured in ways that make interstellar travel fundamentally impractical for biological beings operating on human timescales. This isn't a bug in reality. It's a feature that emerges from the mathematical relationships governing matter and energy. The laws of thermodynamics ensure that energy always disperses, making perfect efficiency impossible and requiring ever larger energy investments for marginal improvements in speed. The second law of thermodynamics guarantees that some energy will always be wasted as heat. No engine can be 100% efficient. The laws of relativity ensure that faster speeds require exponentially more energy, creating diminishing returns that no technology can overcome. As velocity approaches light speed, the energy required approaches infinity. This isn't an engineering challenge, but a mathematical certainty. These aren't engineering problems waiting for better solutions. They're mathematical constraints built into the fabric of reality itself. No amount of cleverness, determination, or technological advancement can violate the fundamental structure of space-time. The universe operates according to differential equations, mathematical relationships that describe how matter and energy behave under all possible conditions. These equations don't contain special clauses for advanced civilizations, or exceptions for species that really want to travel between stars. Light speed represents the speed of causality, the rate at which cause and effect can propagate through space. Events that occur simultaneously in one reference frame happen at different times in others. But the mathematical relationship remains constant and inviolable. This creates what physicists call the light cone, a geometric description of which events can influence which other events. Anything outside your light cone is causally disconnected, unable to affect you or be affected by you until light has time to travel the intervening distance. Similarly, the structure of space-time and interstellar distances confine us within our local bubble, fundamental physics in action always. The final understanding is that we live within a bubble of approximately 1.5 light years of maximum practical radius. Beyond this radius, physics makes it impossible to project meaningful human presence, not temporarily, but fundamentally, probably forever. This represents not a technological challenge awaiting solution, but an absolute boundary imposed by the basic structure of reality itself. This doesn't mean we should abandon space exploration or stop sending probes to increasingly distant frontiers. It means we must adjust our expectations about what remains possible and what will forever lie beyond our reach. The distinction between temporary limitations and permanent impossibilities becomes crucial for planning our species' future. Science fiction sold us the dream of a galaxy populated by humans. Thousands of colonized worlds, vast connected stellar empires spanning light years. Television shows like Star Trek portray casual travel between star systems, where characters hop between worlds as easily as we travel between cities. But fundamental physics suggests this dream represents impossible fantasy, a contradiction with the basic structure of observable reality as we understand it today. The universe wasn't designed for biological beings to spread across galactic distances. It's structured in ways that keep civilizations isolated within their natal star systems. Each stellar system is essentially an isolated island, separated from others by oceans of void insurmountable within human timescales. If intelligent life arises in another star system, we will never meet them physically. The distances guarantee permanent isolation between civilizations. Imagine the tragedy of this cosmic loneliness. Two civilizations might develop simultaneously, just 20 light-years apart, close neighbors by galactic standards. Both might discover radio, develop space travel, even detect each other's signals. Yet they would remain forever separated by distances that make physical contact impossible. Radio signals can travel between stars, but conversation would require years or decades for each simple exchange of messages. A civilization 100 light-years distant would exchange messages requiring 200 years for round-trip communication, making dialogue functionally impossible. By the time you received their greeting, the political system that sent it might have collapsed. The language might have evolved beyond recognition. The technology that transmitted the signal might be obsolete. You would be conversing with ghosts, echoes of civilizations that may no longer exist. And civilizations don't endure eternally. Signals might arrive long after their transmitting civilization has completely disappeared from historical existence. The Roman Empire lasted roughly 1,000 years, but changed so dramatically that early Romans would be foreigners to late Romans. Modern humans would be equally foreign to people from just 500 years ago. Our technology, language, social structures, even our understanding of basic physics would be incomprehensible to medieval minds. Now imagine the changes that occur over thousands or millions of years. The probability of two civilizations existing simultaneously and close enough for meaningful communication remains extraordinarily low statistically. The Drake equation attempts to estimate the number of communicative civilizations in our galaxy, but its parameters are extremely uncertain and speculative. Frank Drake's famous equation multiplies factors like star formation rate, fraction of stars with planets, fraction of planets developing life. Each factor carries enormous uncertainty, making the final estimate range from one civilization, US, to millions. But uncertainty doesn't help us. It reveals how little we truly know. Even assuming millions of civilizations exist, they would be separated by thousands of light years on average, permanently isolated from one another. This creates a profound paradox. The universe might teem with intelligent life, yet each civilization dies alone without contact. Think about the loneliness this implies. Countless species throughout the galaxy, each developing science, philosophy, art, and love, each discovering their cosmic isolation independently. Each civilization looks up at the same stars we see, wondering if anyone else exists, never knowing they're surrounded by others equally isolated. They would face the same questions that torment us. Are we alone? Is there meaning in a universe so vast and empty? Each species would develop its own answers, its own religions, philosophies, and scientific theories to explain existence, yet none would ever share these insights with others. The bubble that confines us isn't a cruel prison, but the natural consequence of a universe too vast for the scale of conscious beings. We are microscopic temporally, living for decades in a universe billions of years old, a temporality impossible to reconcile with observed cosmic scales. Human lifespans represent about 70 years. The universe has existed for roughly 14 billion years. Our entire species has existed for only 300,000 years. We are temporal mayflies in a cosmos that operates on geological and astronomical timescales. We are microscopic spatially. A few trillion cells in bodies that would fit within a galaxy containing trillions of immense bright stars. Our physical extent, even accounting for all human artifacts and influence, remains invisible at galactic scales, less than a single pixel in any cosmic photograph. If you could shrink the Milky Way to the size of North America, our entire solar system would be smaller than a single atom. Earth would be subatomic, and humanity would exist at scales below current measurement capabilities. We are unimaginably small in a universe that exceeds our capacity for scale comprehension. Our civilization spans only a few thousand years, nothing compared to the billions of years of cosmic history that preceded us. The pyramids of Egypt, among our oldest monuments, were built less than 5,000 years ago. The universe was already ancient when Earth itself formed. Stellar evolution operates on timescales of millions to billions of years. Galaxies collide and merge over billions of years. The cosmic microwave background radiation has been cooling for nearly 14 billion years. Human civilization represents a brief flicker in this vast temporal landscape. Everything we have built, all culture, art, science, philosophy, exists within a point smaller than an atom on the universe's scale. Every human thought, every work of genius, every moment of love or discovery, all confined to a mote of dust drifting through infinite emptiness. Yet consider what we've accomplished on this mote. We've deciphered the laws of physics, mapped the cosmos, created symphonies and sculptures that capture the beauty of existence. We've loved, laughed, wondered, and dreamed. All of this emerges from arrangements of matter more complex than anything else we've observed, and yet we are unique within this local bubble, possibly unique within a volume spanning hundreds of light years around us completely. Earth may be the only place within thousands of light years where life developed complex consciousness capable of contemplating its own existence. The conditions required for complex life appear extraordinarily rare. A star of the right type, a planet at the right distance, liquid water, protective magnetic fields, a large moon to stabilize the orbit, Jupiter to deflect asteroids. Hundreds of factors must align perfectly. This makes our existence simultaneously insignificant and precious, beyond any possible measure of absolute value. Insignificant because we occupy essentially nothing in cosmic space-time, an atom of consciousness in an ocean of unconscious empty matter. Precious because consciousness appears rare, perhaps unique. A phenomenon that allows the universe to know itself through us temporarily while we exist. Through human minds, the cosmos becomes aware of its own vastness, beauty, and mathematical elegance. We are the universe's way of experiencing itself. Through our eyes, starlight becomes beautiful rather than merely electromagnetic radiation. Through our minds, mathematical equations reveal the elegant laws that govern reality. Through our hearts, we feel wonder at the cosmic dance of matter and energy. Carl Sagan described Earth as a pale blue dot suspended in a sunbeam, referencing the famous photograph taken by Voyager 1 from the edge of the solar system. In that image from 1990, Earth occupies a fraction of a pixel, minuscule beyond adequate description in common words. Everything we know, everyone we love, all human history happened on that invisible point, lost in the immense observable cosmic void. Every war and peace, every discovery and creation, every birth and death contained within that barely visible speck. The bubble that confines us also protects us. It defines our home, creates the context within which human existence has specific local meaning. We don't need to conquer the galaxy to live meaningful lives or create extraordinary civilization within our naturally established limits. Perhaps accepting limitations represents greater wisdom than the impossible desire to transcend them. Recognition of reality rather than indulgence in fantasy. The invisible wall isn't failure or tragedy, but simply reality, the structure within which we exist and probably always will exist. Within this bubble, we have an entire solar system to explore. Planets, moons, asteroids, resources beyond our needs for millennia. Mars could eventually be terraformed. The moons of Jupiter and Saturn might harbor subsurface oceans with primitive life existing currently. Europa, Enceladus, Titan. These worlds might contain entire ecosystems beneath their icy surfaces. ocean worlds where life could have evolved independently from Earth, we might discover that life is common within our solar system even if it remains impossible to reach life around other stars. The asteroid belt contains trillions of tons of metals, water, and minerals. Resources sufficient to construct thousands of orbital habitats. We could create a vast space-based civilization within the solar system, without ever leaving our local bubble of solar gravitational influence. Orbital habitats like O'Neill cylinders could house billions of people with artificial gravity and complete designed terrestrial environments. Each habitat would be its own world, a sustainable closed ecosystem, a small artificial Earth orbiting the Sun, or major planets of our known system. These space habitats could be more beautiful than Earth, designed specifically for human comfort and happiness. With perfect climate control, stunning vistas of space, and abundant resources, we could build paradise among the stars without crossing interstellar distances. The interstellar limitation doesn't prevent growth. It merely defines the frontier beyond which physical presence cannot realistically extend, and perhaps this is sufficient. Perhaps we should focus on prospering within limits rather than lamenting impossibilities. Human experience doesn't require a conquered galaxy to be rich, deep, and meaningful in its own unique possible dimensions. Art, love, knowledge, compassion, beauty, everything that makes life valuable exists here within the bubble we collectively inhabit. The invisible wall defines our place in the cosmos. Not as a prison, but as home, the context within which we flourish temporarily. If you're still awake, it's because the content was really good. So take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.